Hello, welcome to another module in this massive open online course on probability and random variables for wireless communications. So today let us look at another important concept in probability and random variables, that is a Gaussian random variable. So today we are going to focus on the concept of a Gaussian random variable. And a Gaussian random variable is a very important random variable in the context of communications and wireless communication systems, and it arises very frequently. So, it is important to know the Gaussian random variable and the various properties of the Gaussian random variable, alright. So, the Gaussian random variable, which is also known as the normal random variable, and its probability density function. So, if x is a Gaussian random variable, so let x be a Gaussian random variable, then the probability density function fx of x for this Gaussian random variable is given as 1 over square root of 2 pi sigma square e raised to minus x minus mu whole square divided by 2 sigma square. So, this is the probability density function, this is the PDF, or basically the probability density function for the Gaussian random variable. This is the PDF of a Gaussian random variable, which is f of x equals 1 over square root of 2 pi sigma square e raised to minus x minus mu whole square divided by 2 sigma square. This is the probability density function of the Gaussian random variables, where the quantities mu and sigma are the parameters, and these denote, for instance, expected value of x, or the average of the Gaussian random variable is equal to mu. So, the parameter mu denotes the expected value or the mean of the random variable. So, this is the mean of the Gaussian random variable, and the quantity sigma square denotes the variance. That is, if I look at expected x minus mu whole square, that is equal to sigma square, which is the variance of the Gaussian random variable. So, the quantity mu is the mean, that is the expected value of x of this Gaussian random variable, and sigma square is the variance, that is expected value of x minus mu whole square for this Gaussian random variable. And if I plot this probability density function, if I plot the probability density function of this Gaussian random variable, it is going to look something like this. The probability plot of the probability density function looks like this. Most of you should be familiar with this. The center, the maximum of this occurs at, this is at x equals mu, that is the peak. This is the peak or the maximum. This is the peak of the Gaussian random variable occurs at the mean, that is x equal to, there is a peak or the maximum of this Gaussian, or this probability density function of the Gaussian random variable occurs at the mean, that is at x equal to mu, and the width of this distribution, the width of this curve is proportional to sigma square, that is the variance. So, this this width is proportional to sigma square, where sigma square is the variance, and this is of course this is also known as a bell shape because it looks like a bell. This is also known as a bell shape. The Gaussian probability density function is also known as the bell shaped curve. The bell shaped curve whose center is at the mean mu, and the width of this bell, the width of the Gaussian probability density function is proportional to sigma square, which is the variance. That is, the larger the sigma square, that is the larger the width, that, and sigma square, this variance, as the variance decreases, if the variance is very small, then the Gaussian probability density function is much more peaky, that is its width is much more smaller. All right. And now let us look at another very interesting property, a very interesting and very important property of the probability density function. For instance, Gaussian probability density function is very important in Gaussian is very important in the context of communication. The Gaussian probability density function is very important in the context of communication. For instance, all communication systems suffer from noise degradation, that is noise at the receiver, and very frequently the noise process at the receiver is modeled as a Gaussian random process. The noise at the receiver, that is the noise in the communication system, is modeled using the Gaussian probability density function. So this is one of the most important applications of the Gaussian in the context of, so noise in communication system is modeled as a Gaussian random variable or a Gaussian process, as we are going to see in the next couple of lectures. That this is a Gaussian random variable which is a function of time, which is a random variable at each instant of time, that becomes a Gaussian random process. All right. So noise in a communication system is a Gaussian random process. At each instant of time, it is a Gaussian random variable. Further, specifically in the context of a wireless communication system, the fading channel coefficient is also modeled as a complex Gaussian random variable. That is a complex quantity with the real part and the imaginary part distributed as independent Gaussian random variables, that is known as a Rayleigh fading channel coefficient. So specifically also in the context of a wireless communication channel, in the context of a wireless communication channel, it is modeled as a complex Gaussian random variable, and this leads to what is known as a Rayleigh complex Gaussian random variable. The wireless fading channel coefficient is modeled as a complex Gaussian random variable, that is a complex random variable whose real part and imaginary part are Gaussian random variables, and the amplitude of this fading coefficient can then be modeled, can then follows a Rayleigh distribution, right. So Gaussian is very important in the context of both conventional communication systems, because the noise process at the receiver is modeled as a Gaussian, as well as in a wireless communication system, because typically the channel coefficient, the fading channel coefficient, is modeled as a complex Gaussian random variable. Further, Gaussian with mean mu and variance sigma square is also denoted as a Gaussian with mean mu and variance sigma square. This is also denoted as n of mu comma sigma square. So a Gaussian with mean mu and variance sigma square is also denoted using the notation n of, that is the script n, the calligraphic n of mu, which is the mean, and sigma square, which is the variance of the Gaussian random variable. Let us now look at another very interesting and practically very important property of the Gaussian random variable. So let us look at another important property of the Gaussian random variable. So, another important property of the Gaussian random variable, that is, if I look at a linear combination of Gaussian RVs, Gaussian random variables, that results in another Gaussian random variables. That is, whenever I take a group of Gaussian random variables and consider a linear combination, a linear transformation of these Gaussian random variables, the resulting random variable is another Gaussian random variable. Therefore, linear transformation of a bunch of Gaussian random variables results in another Gaussian random variables. So, and this is a very important property of the Gaussian random variable. All right. So, let us illustrate this mathematically. So, what do we mean? So, let us say we have a group of random variables. Let us consider x1, x2 up to xl. Say these are L Gaussian random variables. So, these are L Gaussian random variables, such that we have expected value of xi, that is the mean of each of these is mu I, and the variance, that is expected value of xi minus mu I whole square equals sigma I square. That is, we are considering L Gaussian random variables x1, x2 up to xl, such that the mean, that is expected value of xi is mu I, and the variance expected value of xi minus mu I square is sigma I square. Therefore, I can denote the Gaussian random variable xi as script n brackets mu I comma sigma I square, using our notation for the Gaussian random variable defined just a while ago. So, we have xi is a Gaussian random variable. I can denote xi as n mu I sigma I square, and further the covariance, let us define another new quantity known as the covariance. That is, if I look at expected xi minus mu I times xj minus mu j, where I is not equal to j, this is equal to sigma ij. This quantity is also known as, the covariance of this Gaussian random variable, that is expected value of xi minus mu I times xj minus mu j, that is expected value of the product xi minus mu I and xj minus mu j. This is known as the covariance of the random variables xi comma xj, and that is equal to, we are saying that is equal to sigma I comma j. This is the covariance of xi comma xj, and this is equal to sigma ij. Now, let us consider the linear combination of these random variables. Consider x defined as a linear combination of x1, x2 up to xl, that is, we have a linear combination of these Gaussian random variables, that is x equals a1 x1 plus A2 x2 plus so on up to AL XL. So, what we are doing is we are linearly combining these Gaussian random variables x1, x2 up to XL. How are we combining them? We are generating a new random variable x as x is equal to A1 times x1 plus A2 times x2 so on up to AL times XL, where A1, A2, AL are the weighting coefficients, and this is known as, since we are combining them linearly, this is known as a linear combination. So, this is a linear combination of L Gaussian RV. So, this is a linear combination of L Gaussian RV. So, x is a random variable which is a linear combination of L Gaussian random variables, and using the previous property we have said that the linear combination of a group of random variables results in another Gaussian random variable. So, capital X, which is a linear combination of x1, x2, xl, is another Gaussian random variable. So, x, so such a random variable x which is generated as a linear combination of Gaussian random variables, x is in turn a Gaussian RV. Further, let us find now the mean and the variance. So, we want to find the mean of x, that is, what is the mean of this new Gaussian random variable x, what is the variance of this new Gaussian random variable x. So, what we want to do now is we want to find the mean of this Gaussian random variable x, which has been generated as a linear combination of x1, x2, xl, and the variance of this Gaussian random variable x, which has been generated as the linear combination of these Gaussian random variables. Okay. So, let us start by finding out the mean. The mean of this Gaussian random variable mu equals expected value of x, but x is in turn summation over I ai xi, because x is a1 x1 plus a2 x2 plus so on up to al xl. Now, the mean is, expectation is a linear operator, so I can take the expected operator inside. So, this is I summation over I expected value of ai xi. That is, what do we mean when we say that the expectation operator is a linear? We are saying the expectation of a sum of random variables is the sum of the expectations of the random variables. Therefore, I can take the expectation operator inside the summation, and therefore, now I can write this as, we know expected value of each xi is mu I, therefore, this is equal to summation ai times mu I. So, our mean of this random variable is summation ai mu I. This is also the expected value of this random variable x. So, we are saying that the expected variable, we are derived that the expected value of this random variable x equals summation ai times mu I, which is being denoted by mu, which is the mean of this Gaussian random variable, is the mean of this new Gaussian random variable capital X. Okay. Now, let us compute the variance, which is much more tricky. The variance is sigma square, which is the variance, that is the expected value of x minus mu whole square. This is the variance, which is equal to, now let us substitute the expression for both x. Expression for x is summation over I ai xi minus summation over I ai, the mean, remember mean is ai mu I. So, I am substituting for mu as ai mu I whole square, which is basically the expected value of, in brackets, summation over I ai xi minus mu I whole square, which can now be simplified as this is equal to the expected, let me write it, expected value of this can be written as expected value of summation of I ai xi minus mu I times summation over j aj xj minus mu j, that is the product. So, the expected value of summation over I ai xi minus mu I whole square is expected value of summation over I ai xi minus mu I times the summation over j aj xj minus mu j. I am just rewriting this quantity again by changing the index from I to j, so that basically I can take the product and compute the expectation of the product. And now what we have is something very interesting. Now I have this is basically the expected value of summation I summation j ai aj xi minus mu I xj minus mu j. This is the expected value of this quantity, and now I can split this summation over I comma j into two parts. One is all such terms when I is equal to j, such terms reduce to when I is equal to j, we have ai square xi minus mu I whole square, and when we take the expected value of those terms, we get expected value of xi minus mu I whole square, which is sigma I square. And terms with which in which I is not equal to j, such terms we have ai aj xi minus mu I times xj minus mu j. When I take the expected value of that term, it reduces to ai aj expected value of xi minus mu I times xj minus mu j, which is basically ai aj sigma I j. Okay. So, we have two terms. So, we have two kinds of terms. One, when I is equal to j, those terms reduce to expected value of ai aj expected value of xi minus mu I whole square, plus terms for which j is not equal to I plus summation over I summation over j, j not equal to I expected value or ai aj expected value of xi minus mu I times xj minus mu j, which is equal to, now you can see this is basically xi, expected value of xi minus mu I is sigma I square, expected value of xi minus mu I times xj minus mu j, this is the covariance sigma I comma j, sigma of I comma j. Therefore, this is equal to ai square when when I is equal to j, this is ai square sigma I square plus summation over I summation over j, j not equal to I ai aj sigma ai aj sigma I j, and therefore, what we have is this is basically sigma square. This is basically the quantity sigma square. So, we have calculated the expression for the variance sigma square of this Gaussian random variable x, which is generated as the linear combination of the Gaussian random variables x1, x2 up to xl. Therefore, we are saying the mean of this Gaussian random variable x is summation I ai mu I. the variance is summation over I ai square sigma I square plus summation over I summation over j not equal to I ai aj times sigma I j. Therefore, the Gaussian random variable x can now be represented as x is Gaussian random variable. I can represent it as using the script n followed by the mean, that is summation over I ai mu I comma variance, which is summation over I ai sigma I square plus summation over I summation over j not equal to I ai aj sigma I j. So, this is the Gaussian random variable, this is the mean mu of the Gaussian random variable, this is the variance sigma square of this is the variance sigma square of this Gaussian random variable x, which is generated as a linear combination of these Gaussian random variables x1, x2 up to xn. So, what we have done is we have considered this Gaussian random variable, which is basically a linear combination of the Gaussian random variables x1, x2 up to xn, and we have calculated the mean and this variance of this new Gaussian random variable x in terms of the means, the variances and the covariances of the Gaussian random variables x1, x2 up to xn, and this we said is a very useful result, especially in the context of communications and wireless communications, which one has to invoke frequently, because the noise process of the receiver is Gaussian, and also several interesting things, for instance, such as the channel coefficient, the relay fading channel coefficient can be modeled as a complex Gaussian random variable with real part Gaussian and the imaginary part also Gaussian. So, this comprehensively clarifies the probability density function and various key properties of the Gaussian random variable. So, we will stop this module here and explore other aspects in the subsequent modules. Thank you very much.